So our first talk today is a low-cost helmet-based non-invasive ventilator for COVID-19. It's being presented by Dr. Yasser Khan. Yasser is a postdoctoral scholar at Stanford University. He is advised by Professor Janan Bao in chemical engineering and Professor Boris Merman in electrical engineering. Dr. Khan completed his PhD in electrical engineering and computer science from the University of California, Berkeley. He received his BS in electrical engineering from the University of Texas at Dallas and his MS from King Abdullah University of Science and Technology. Dr. Khan's research focuses on wearable medical devices with an emphasis on skin-like soft sensor systems. He received the EECS Departmental Fellowship at UC Berkeley, Discovery Scholarship and Graduate Fellowship at KAUST, and Academic Excellence Scholarship at UT Dallas. Welcome, Yasser.
Thank you for the introduction, Angela. I will start sharing my screen. Can you see the screen?
Yes, we can see it now.
Okay. Hello, everyone. Today, I'll be talking about the story of making non-invasive ventilators for Bangladesh. The reason I'm saying it's a story because it's not a typical research presentation. We had to change a lot, adapt to the real situation, and that's why it became a story. And I'll be talking about basically the solution we are proposing for Bangladesh in terms of ventilation. Okay, I believe most of you are familiar with Bangladesh. Here, in the situation of COVID-19, the most important factor is the population density in Bangladesh, because we have roughly 170 million people, and the land area is roughly 57,000 square miles. So to put that in perspective, if you take half of US population and put that in Illinois, that will give you the same population density of Bangladesh. Now, we had our first case on March 7th, and then the government was fast, and they imposed the lockdown measures on March 22nd. And this what happened in March 23rd. So people started leaving the capital, Dhaka, to the rest of the country. So what that did effectively is spread the disease. And here you can see social distancing is something we are using in the Western countries as a measure to prevent the spread of disease. It will not be as effective in countries like Bangladesh, where we have a high population density. Apart from that, there are socioeconomic challenges we are facing. Let's say one of the major industries, garments, and people working in garments, they cannot work from home. So that's why we cannot impose these lockdown measures for months, and we have to think about other approaches. And so right now we have roughly 40,000 cases, and it is increasing. So here I'm showing the number of positive tests. The daily test we have is maxed at 10,000, so we cannot go beyond 10,000 tests a day. And the alarming part is the number of positive tests. It's now closing into 20%. So it is spreading steadily. So that's why it's quite challenging in countries like Bangladesh and think about the ventilation needs. Next, I'll talk about ventilators, because I believe everyone heard about ventilators for COVID-19, because it's a respiratory disease, and the tool that provide respiratory assistance to people is ventilators. But here I'm showing two different types of ventilation: invasive and non-invasive. In invasive ventilation, you will have the endotracheal tube inserted, and that's why it's called invasive. And here you need to control the air pressure and flow quite well. In terms of non-invasive ventilation, here you don't put the tube inside the body, rather you use a face mask. So the reason I'm showing these two types of ventilation, because most of the ventilators now designed for COVID-19 is focused on invasive ventilation. And there are quite a few pros and cons between these two. First, if you use mechanical ventilation, there are reports that you will develop ventilator associated pneumonia. There are cases in terms of that. And then you have to sedate the patient because there's a tube going inside and the patient won't be conscious. And the amount of sedation will actually, there is a chance that it can, if it's not controlled, it will lead to brain dysfunction. And also intubation related complexity increases mortality and morbidity. In the non-invasive case, so here the patient is at the early stages of COVID-19 or the respiratory disease. So here you can actually use the non-invasive measures. And there are reports saying that if you use these non-invasive measures, you can reduce complication by 50%, also shorten the hospital stay, and increase the quality of life. Here I'm giving the overview of these two. But if the patient goes into critical situation, then the non-invasive shouldn't be considered. The patient needs to be intubated and put on mechanical ventilation. So this is the last resort that medical professionals use. We saw the same thing as I listed before for invasive ventilation. There are reports from London and also Italy saying that people put on mechanical ventilation for COVID-19 are showing extremely high mortality rates, close to 65%. So in that case, we are thinking about what other options do we have, and non-invasive ventilation is one of those. Here, I'll be talking about the ventilation need in Bangladesh. Right now, we have a dedicated COVID hospital. So not all the hospitals in Bangladesh are treating COVID patients. So that's why the ICU capacity is quite limited. What do I mean by ICU capacity? See here, this is the ICU setting when the patient is sedated and has a endotracheal tube inside. You need all this machine to monitor the patient, and it's only available in ICU settings. But in countries like Bangladesh, where we have limited resources, we don't have the ICU capacity. So even if you make a lot of ventilators, the ICU capacity, also trained personnel to run these tools. What we have is essentially movable oxygen cylinders, and also we need these to be easily operable and portable. So here I'm showing a video. This is a reporter. She's showing inside a COVID dedicated hospital in Bangladesh. So this is from early in the time. So it's I think in April. That's why they were setting up the beds, and you don't see that many people inside. But it gives you an impression of what are the available resources. So here you will have rows of beds, and then you will have these movable oxygen cylinders. So this is a dedicated hospital for COVID, and these are the resources we have. And moving farther into this, we won't have similar hospitals. What we will have is this sort of field hospital type solutions where there will be only available hospital beds, and we have to design our ventilators for that. So it makes the designing designing ventilators for Bangladesh quite different from what we are doing in the US or other developed countries. So right now we came up with the idea that we need non-invasive ventilation with face mask. But once we started looking into this, what we saw is if you go into non-invasive ventilation, these are essentially face masks. And once you have a high pressure air coming in, it aerosolizes the virus. Elon Musk, he initially proposed using non-invasive ventilation for COVID patients. And he faced a backlash in Twitter's. And people were saying, if you use CPAP or BiPAP machines, you will hear CPAP and BiPAP. CPAP means continuous positive air pressure. These are essentially pressure devices. It puts high pressure through the face mask, and that results in aerosolization of the virus. And we got stuck. So our plan was to create a non-invasive ventilator, and then we faced this problem where we have to design something that doesn't aerosolize. And we have been looking quite a lot, and we found a unique solution where you can contain the virus if you use a helmet. So here, these are two results where people are using uh, aerosol, and you can actually visualize the aerosol generation. And here for the face mask, you can see it spreads quite a lot. And if you use a helmet, you get the aerosol contained. So once we had this, we were talking to doctors in Bangladesh. They had the exact same concern that if you use a CPAP or BiPAP machine to do non-invasive ventilation, we will run into aerosolization problem. So that's why once we proposed that we can use a helmet, they were much comfortable using the device we designed. Now, so here I'm talking about the current efforts. So there are quite a few ventilators right now that are using these Ambu Bags. So here, this is a Ambu bag. These are used in critical situations, and let's say you don't have any other option, and then the medical professional will use this breathing device and squeeze this. So these are bags that you can squeeze, and that generates the flow. And what MIT did is they had a project in 2010, and they mechanized this Ambu bag. And that was that what essentially started all these rapid response ventilators using these Ambu bag designs. But the problem here, you can see there are many moving parts here. And just mechanically pushing this bag, it's not precise. So you will run into a problem in terms of reproducibility. And also there are many, many moving parts. And these are quite difficult to assemble and use. And one example I'm giving here is this is actually done in India. And they implemented the similar design with Ambu bags, and they deployed 1,000 units. And the feedback they're getting from the doctors are not good. What they're saying, this is not living up to the benchmark you would need for of keeping a patient alive for days. So this is something you will use for a couple of hours, something like that. So there are quite a few challenges for these rapid response ventilators. And keeping all this in mind, we decided that we have to come up with another solution that is non-invasive. Also, it contains the spread of virus. So here we designed the non-invasive ventilator. Essentially, we have a DC blower. So this blows in air. And also we have the control electronics associated with the device. We can mix room air and oxygen and deliver to a patient. And we had to look into how can we create a good interface. So we had to add a viral filter so it doesn't spread the virus, and also a PEEP valve. So this essentially controls the pressure within the helmet. And here we have the photo. Essentially, you have a microcontroller unit controlling the whole device. We have a real-time clock that maintains the time, even if it's disconnected from a power source. And then we have a SD card that records all the data. Essentially, it's like a black box for this ventilator. And then we have an easy-to-use touchscreen display. We also need to put in sensors to look at the pressure and flow. And we have the DC blower. Also, we were thinking about adding a oximeter to know what's the SpO2, the oxygenation of the patient. And then we have a motor controller to drive the DC blower. So this is the final product, but we had to go through 3 different designs and burning many motor controllers and also blowers to find out what actually works. One of the biggest problem now is to find parts that those are available. So right now, one example is we had a pressure sensor, we designed everything for that one, and then when we ordered the board came in, we were looking for the part. They had 1,000 units in stock, but it was out of stock overnight. So we couldn't get the pressure sensor. So this is one of the challenges while designing during this COVID-19 situation. We also have a user interface. So this is a easy to use user interface, and I'm showing the whole setup here. It basically is the NIV system, and then you need tubing and the helmet. So this is quite easy to use. We don't need ICU professionals to use this device, and also it's easily deployable. We can run in 2 different settings, as I mentioned, CPAP and BiPAP. I'll talk about that later. And also flow rates is quite important. You need a decent flow rate, because if inside the helmet, if you don't maintain that flow, there is a possibility of CO2 rebreathing. So that's why we needed to do experiments to find out what is the minimum flow rate. And also we can do the pressure profiles from 5 to 20 centimeter of water. IE ratio is essentially inspiratory to expiratory cycle ratio. And also we can do different breaths per minute. And it has a alarm for monitoring leak and disconnection. And the whole thing fits inside a 8-inch by 8-inch by 4-inch box. It's super portable. And another thing is we can easily fabricate this device. So all these devices I actually fabricated in one sitting. So in one night, I was able to assemble 5 of this. So these are easily fabricable. Here I'm showing some technical data. I'm not going to go much detail into it. Essentially, you control the blower PWM control signal that gives you the different pressures we need. And also we saw that we can control the flow by having a different pressure difference. And as I mentioned, we made 5 devices, and we had to check the reproducibility. And we did a batch calibration, so it's not device to device calibration. For one batch, we just use this calibration curve. And what we saw is we can actually get good amount of reproducibility even from device to device. Same goes for flow. We can do 60 liters per minute, 100 liters per minute, and 140. And also we tested the unit for 5 hours. So here I'm showing its running time is 5 hours. We can even go higher. It's just I had to shut it down because it was getting late at night. And we were getting good pressure profile throughout this whole 5 hours of testing. Then here I'm showing the BiPAP mode. In CPAP mode, that's the continuous positive air pressure, you will have one flat line pressure. In BiPAP mode, what happens is you have 2 different profiles in the inspiratory and the expiratory. It essentially helps the breathing. So when you are exhaling, it reduces the pressure. And there are a bunch of different settings you need to apply depending on the patient. And we showed that we can actually get different EPAP profiles. Also, we can vary the breaths per minute, and also IE ratio. So these are essentially what you will get in a commercial BiPAP machine. And then finally, we tested on a person, and here I'm showing the different flow rates. So here I set the pressure at 5 centimeter water, and this is at a low flow, below 60 liters per minute. And here you will see some sort of fogging of the helmet. But if you increase the flow over 60 liters per minute, it becomes much more comfortable for the patient, and it is usable. And we actually followed NHS UK guideline for the treatment protocol, and we are actively working with doctors to come up with a modified guideline for this helmet-based NIV. So I'll be really happy to talk to you about if you have some suggestion in terms of what should be the treatment protocol. And finally, this is the video of the device here I'm putting on. So you see this is the helmet, and here we have the vital filters and the PEEP valve, and this is connected to the NIV system here. we will briefly see. And once the machine is started, you will see the helmet gets pressurized. So this is the NIV system. It's running in CPAP mode. And so far, it's working quite well for us. And we are planning to take this to clinical testing. We are now working with doctors in Bangladesh for testing. And also, we are continuing to test and update the system. And we recently joined the broader Stanford ventilator team, so we can make this accessible. So this link you can click and you get the preprint version of the paper, because we wanted to get this out as soon as possible so other people can use it. So I'd like to thank the Bangladeshi students and alumni of UC Berkeley and Stanford who funded this project. I basically reached out to them saying that we have a dire need and we need your help. And so far, no one let me down. So that's the highlight of this project. And also I'd like to thank Zanan, Manu, who have been encouraging and giving guidelines. And this is essentially a lot of people got involved in this project, and I would like to thank all of them. Thank you so much. If you have any questions, I'll be glad to take those.
Wonderful. Thank you so much, Yasser. And we have had comments just praising you for your efforts. And a couple questions have come in. There are two here that are wondering about the seal around the neck. Could you speak to that?
Yeah, so the seal it's a rubber seal. You can think about a turtleneck made out of rubber. And you need to cut the seal if it's too tight. But other than that, we in the team wore the device. It's not that uncomfortable. So it's a good seal. It's a rubber turtleneck, and it holds up to the pressure you would need for ventilation. Yeah.
Great. And another question around heat retention in the helmet. Does it get hot in there? And I'm wondering if in climates like Bangladesh, it might be more humid. And does it fog up?
Yeah, exactly. So that's a really good question. It feels like you have a air conditioner for your head, because you have a really good flow. If you don't have the flow, it gets you will have moisture formation. But with the good flow, it is comfortable. It's basically you're carrying your air conditioning unit with you.
Fantastic. That does feel sound like it feels great, and certainly very much needed in these times. Yasser mentioned his paper. If you look on the announcement for this webinar, I also have a link to his research paper there. And feel free to reach out to me, angela.mcintyre@stanford.edu, if you have more questions for Yasser. We'll now switch over to our next set of talks.